evening. Nice to be back after a very nasty bout of food poisoning that made me miss my only Sky at Night programme in 47 years. But I'm grateful to those who stood in for me and to the hundreds of people who sent me get well cards. I'm truly grateful. I'm replying as soon as I can. So this evening, back to the Cassini probe to Saturn. First of all, with Chris, some news notes. And first of all, the Perseid meteors. We get these every August, but this year the Perseids may be really good. We're going through a rich part of the stream, and the moon's out of the way. Maximum August the 12th, so they could be quite spectacular.
That's right, best seen after midnight, and the Perseids are always reliable for nice, bright meteors, so it should be obvious to anyone looking up in the sky.
And from meteors to comets. Interesting thing here, Comet Wild.
That's right, our second ever close-up look at the nucleus of a comet provided by the Stardust probe, which has flown round Comet Wild and is returning to us with material. Gets back in January 2006. But in the meantime, we've got these stunning images of the nucleus of the comet.
Quite.
Now, Giotto went to Comet Halley,
Indeed.
and we saw a dirty snowball, fairly amorphous, smooth, icy surface. Whereas this is completely different. There are pinnacles, there's a crater a kilometre across, whereas the comet itself is only 5 kilometres across. Totally unexpected and quite spectacular images.
Full as provided. And of course, Mars is still in the news. The American probes, Spirit and Opportunity, are going strongly and sending back amazing results. Look at this picture sent back by Opportunity from inside Endurance crater. And this channel must have been cut by water. And of course, the atmosphere. We detected methane, and now we found ammonia too.
That's right. Mars Express has found small and significant quantities of ammonia in the atmosphere of Mars. And they're quantities which must be being replenished from somewhere. Now, there are only 2 known sources of ammonia, active volcanoes or small microbes.
Yes.
So this could, I say could, be the first signature of life on Mars. We need more investigations, but this is highly significant results. The first suggestions, perhaps, that there is still life on Mars.
I wonder. And don't forget, those probes are going on working. We'll get more results back yet. So
Absolutely.
We'll wait and see. Chris, thank you very much.
Thank you.
And now, on to our main theme, the Cassini probe at Saturn. And Saturn, the giant planet, is now emerging into the morning sky. It's a huge world, more than 800 million miles from the Sun, diameter more than 70,000 miles. Of course, quite distant from the Earth. A gaseous globe and that lovely system of rings. Here's a drawing I made some time ago with a fairly small telescope. And that's the kind of thing you'll see when Saturn becomes visible in the morning sky once more. And now, of course, Cassini has got there. And I'm delighted to be joined by 2 people very much concerned on the entire mission, Professor John Zarnecki and Professor Michele Dougherty.
Hello, Patrick.
Well, first of all, John, Huygens is going well.
Indeed it is, Patrick. In fact, since we last spoke, we've actually switched the Huygens probe on just a couple of weeks ago. This was the first time we've done that since it's been in orbit around Saturn.
Was this still attached to Cassini?
It is, of course, and we did a checkout where we run through some of the sequences that we will be doing for real in January at Titan. And I'm pleased to say that everything looks fine. The instruments seem to be in good shape. They've survived the insertion into Saturn orbit, as of course we expected.
Just after our last programme, Cassini went through a gap in Saturn's rings, and the results were quite as expected, were they?
No, there were several surprises. One of them in particular, which I think is fascinating, was actually predicted some years ago. Our old friend Carl Murray from London University and his colleagues wrote a paper 4 or 5 years ago, and they predicted that the passage of, for example, Prometheus, one of the satellites that passes very close to the ring material, would actually have the effect of pulling out some of the dust particles in the rings. And in fact, we can see that in this image, very faint sort of line, the streamer they call it, between Prometheus and the ring. And that is pretty much as they had predicted. It's gravitationally perturbing the material as the satellite passes near to the ring.
It's an amazing picture, isn't it?
Oh, it's beautiful, really is. And it's the type of thing that makes you realise that it's worth making predictions as to the type of things that we're going to observe when we get to different planets, because once we get there, to be able to see that we were able to predict this is really very exciting.
And now, of course, we have magnificent pictures from close range. Look at this one. It shows the rings in all their glory, these many divisions and tiny ringlets. What do you think about that, John?
Well, of course, we have to realise that these colours that we're seeing are false colours. It's not exactly how they appear visually. This image is from the ultraviolet instrument on Cassini, and it's been constructed to show the variation of composition. Now, this is particularly interesting because it seems, and we decipher this from the ultraviolet spectrum, that there are compositional differences. The blue here represents water ice, but it seems that some of them have a different composition, and so the red colour represents probably contamination with iron or carbonaceous material. And you can see there's a tremendous variation in it. It's a very, very fine structure, and there's perhaps some process which is ordering the particles according to their composition. So there's a lot of detail in here, and it'll be probably several years until this is completely understood.
I remember the first image of the Saturn coming back from Voyager showing these many narrow divisions and ringlets. That was totally unexpected. Have they been thoroughly explained even now?
Oh no, I don't think so. I think the first images we've seen of the rings from Cassini have opened up more questions than actually answering them. One of the things that we don't really understand is the fact that there seems to be some dirt particles between these gaps in the rings. The gaps that we can see, the visual imaging mass spectrometer and the ultraviolet instrument seem to be implying that there is some type of dirt material in this gap, and that's something that we really don't understand at all.
In fact, we found out from the RPWS instrument, that stands for Radio and Plasma Wave Science Instrument, there was in fact a very large number of tiny particles, micron-sized particles.
Made up of ice?
Ice, some of them perhaps contaminated with rocky or carbonaceous material. But we have this wonderful simulation here, and if we have a look, we can see this passage through the supposed gap. In fact, there was something like about 10 to the power 5, that's 100,000 impacts on the large antenna, the large dish, which was turned in order to protect the spacecraft. And we can hear on this simulation the impact. It's like a hailstorm or a sandstorm.
How was that noise produced?
Well, in fact, this instrument detected the little puffs of gas, the plasma produced as these tiny particles hit the spacecraft, and it picks up the signature of the plasma produced, and that's been turned into sound.
But I think what these first results are showing is that 99% of the ring particles are made up of ice and water ice. It's the 1% of the composition that we don't really understand. And that composition seems to change depending on where we're actually looking in the rings themselves. Close to Saturn, it seems to be made up more of iron. As we move further away, we can start seeing carbon dioxide as well. And so this is something all the different teams are going to be working on to try and understand.
I remember the time when we thought the main division, the Cassini division between the two bright rings, was entirely empty, and of course it's not. So
it certainly isn't.
We're learning more about the rings all the time.
We are.
And what we're also seeing is some tremendous structure. We can see, for example, in this image here, a sort of scalloped edge to the rings, and that is presumably due to gravitational interaction between one of the shepherd moons and the ring material itself. So there really is tremendous amount that is coming out, and it's still, of course, early days. We have just literally got days worth of data, and in fact there's going to be at least 4 years worth of it.
And I think one of the really exciting prospects is some of the close-up views that we've had of the rings after Saturn orbit insertion show very fine detailed structure, with the implication being that when we get even better images, we're going to see even more fine detailed structure. So at the moment, we're looking at the edge of the resolution of the camera, and as we get closer, we're going to see even more.
Let's come now on to Saturn itself. This huge globe on average, less dense than water. So have you any real idea what the central core is like?
No, we don't. And what we're hoping to be able to do is with the internal magnetic field measurements and with gravity measurements on these different flybys that Cassini will do at Saturn, is we'll be able to infer what some of the properties of both the core are and the different liquid layers above the core. The pressure at these depths where we think the different liquids are is so strong, so high, that we can't actually produce those type of pressures on Earth. So we've never been able to measure the properties of fluid metallic hydrogen, which we think is close to the center, because we can't produce pressures and temperatures high enough on Earth to be able to actually observe that in the lab.
What are the basic facts about Saturn's magnetic field?
The most important thing Saturn's magnetic field does is essentially protect Saturn from the effects of the solar wind. There is a continuous plasma that blows off from the sun, known as the solar wind, and it streams radially away from the sun, and it hits all the different planets as it moves out through the solar system.
Including the Earth, of course.
Including the Earth. And this view that you have in front of you here shows an image of the cavity, the magnetosphere that forms around any planet as a result of the interaction of the internal planetary field and the solar wind. And as you can see in the picture, there are different boundaries that form. The solar wind flows away from the sun at supersonic speeds, and for it to be able to flow around a body like Saturn, it needs to slow down. And so the first boundary that you see is called the bow shock. This is essentially a shock wave that forms upstream of Saturn and allows the solar wind plasma to slow down and stream round Saturn. The second boundary that we see is known as the magnetopause, and that's the boundary that separates planetary magnetic field and plasma from solar wind field and plasma. And it's the magnetospheric cavity that the Cassini orbiter, the Cassini-Huygens orbiter, is going to spend most of its time in.
Well, Saturn may look calm, but the atmosphere is in fact very turbulent.
It is indeed, Patrick. We know that we have complex motions of the atmosphere, very high winds, and of course we have weather systems. Cassini picked up some of this, and we have this fabulous sequence here where we can see two separate storm systems, and we actually see them merging together to form a single system.
And of course occasionally we see white spots due to uprushes of material from below. The famous one, 1933, which I remember well, discovered by Will Hay, the comedian, who was a very good astronomer. There was a much smaller one in 1961 that I actually found, which didn't develop, and then in 1991 another. So these white spots do occur, but of course nothing like the activity we see on Jupiter, and nothing resembling Jupiter's red spot. Saturn is a calmer world. Well, the globe and the rings, they're providing information and many surprises. And of course, don't forget the satellites not being really examined yet. The most interesting one clearly is Titan, a world which is of planetary size, actually larger than Mercury, with a dense atmosphere, was made up largely of nitrogen. And got pictures of that, John.
Yes, we do. And I shouldn't really be saying this, Patrick, but I'm actually pleased that it's still mysterious. We have some observations from the relatively close, or well, third of a million kilometre flyby early in July. Now, there is some controversy about what these results mean. You can see in these images perhaps some indication of a circular feature, which perhaps is a crater, perhaps, and another linear feature, which some people are interpreting as a valley, some sort of linear feature. But it's still, we just don't know.
Well, Huygens separates from Cassini on Christmas Day and then lands on Titan in January. What's he going to find? Is he going to find a chemical ocean, or ice, or sludge, or what?
Well, we're prepared for all of those, Patrick. What we are finding out is, if you look in this image here, this does seem to show certainly clouds. There is a cloud system here, and you can see in these images, which cover a time span of about 4 or 5 hours. These cloud features do seem to evolve. You can see, though they're slightly murky, you can see some clouds disappearing, others forming. So it does seem that we have weather, we have meteorology taking place. These are probably methane clouds, not water vapour as on Earth. But this does seem to have some similarity to cloud formations that we have on Earth. So we're certainly going to be going through weather systems as we descend through Titan's atmosphere.
What about the magnetic effects near Titan?
One of the things I'm particularly interested in is to see whether Titan has a magnetic
Yes.
field of its own. I don't think it will have an internal field. But what you might see is there might be currents flowing beneath the surface of Titan. Those currents will generate a field which we will be able to measure as we fly past Titan. But another interesting thing about Titan is that you can find it in different plasma environments. It orbits at Saturn at 20 planetary radii. And so when it's on the day side of Saturn, depending on the conditions in the solar wind, sometimes you'll be in the magnetosphere, sometimes you'll be out in the solar wind, and sometimes you'll be in the magnetosheath region, that region where the solar wind slows down and is actually heated up as it flows past the cavity of Saturn. And so what we'll see at Titan is 3 different plasma environments, and we'll be able to observe how all of those plasma environments differ.
I wonder what Titan's really like. After all, the only planetary satellite to have a substantial atmosphere, but a strange world indeed. And we'll know, we hope, in January, if all goes well. When actually Huygens lands there, how long have you got while it's still transmitting?
Well, we have something like 2.5 hours of descent under the parachute through the atmosphere. We then either bash or splash down on the surface. We are pretty confident that we will have something like 2 hours worth of data then. That's the time for which the data link between Huygens on the surface and Cassini, which will be flying overhead, will exist for. Then the link will be lost, and the data which Cassini has been gathering from Huygens will then be transmitted down to the Earth. So that will be something like maybe 5 hours after the data has been collected, and we'll be sitting there at the operations centre in Germany on tenterhooks, waiting for our moment of glory, we hope.
I'm sure you will. Other satellites? Well, last month we showed the outer one, Phoebe, which is a curious kind of world, almost certainly an escapee from the far-flung Kuiper Belt, our solar system. And now Cassini sent back this lovely picture of the icy satellite Mimas with a huge crater there. It's interesting, isn't it?
It is very interesting. And it was quite a distant flyby. During the rest of the tour, we're going to be getting much closer to all of the icy satellites, and so we'll be able to take a much closer look at the surface of them.
And Cassini sent that picture of Iapetus, half bright and half dark. What that dark deposit is, we don't yet know. And Tethys, which is almost entirely an ice floe, with again a large crater.
Yes, these are really tasters, because we've got these were flybys at I think 1.5 million kilometres, something of that order. And of course, over the next 3 or 4 years, we've got many flybys of several of these icy satellites, some at really very, very close distances.
So there are a lot to look forward to. We've had only a few weeks really of data so far.
That's right.
And you have 4 years ahead of you. Are you both looking forward to it?
Can't wait. I mean, the data that we've received as we approach Saturn and during Saturn orbit insertion is really very exciting. We don't understand some of it, and we're going to be learning a lot more as we go through, and I just can't wait for all of the new data to come down.
And many of these instruments are very, very complicated, and there are many subtle effects. So, of course, one is still trying to understand exactly how they work, to get the calibration understood and sorted out. And so there's an enormous amount of work going on in the background to get this basic understanding done.
And I think to get the best understanding possible, we're going to need to put all the different data sets together. And so what the teams are doing at the moment is trying to understand their own data, and once we have an understanding of that, we'll then start combining the data sets.
And you look forward to your coming back to the sky at night quite often and telling us what's going on.
Thank you very much.
Michele, thank you very much.
Thank you.
When I come back next month, I'll be talking about robotic telescopes at Liverpool John Moores University. So until then, good night.